So now we are ready to design combinational circuits. So I'm going to talk about combinational circuit design in general, but later I'm going to show you some examples about how we can design arithmetic circuits. Okay, I'll talk about adders and so on. So we'll see like different designs. So it becomes now more interesting. The course becomes more interesting when we start designing circuits. So the question is, how do we design a combinational circuit? Okay, this is the outline of this presentation. I will show you some examples. For example, to design a BCD to XS3 code converter. This is one example of a design. How we can design a BCD to a 7-segment decoder. What's the meaning of hierarchical design? What's the meaning of iterative design? So these are strategies, okay, for designing large circuits. We have seen combinational circuits before. I already have introduced that before. So a combinational circuit can have n inputs. Okay, so n can be large. It might have actually a large number of inputs. So we can number them x1, x2, all the way to xn. And it can have a large number of outputs, for example, m outputs. And each output is a function of the inputs. So we can number these outputs as function 1, f1, f2, f sub m. So these are m outputs. And each output is a function of the input variables. And it depends on the values, the present values of these inputs. So it only depends on the inputs. Okay, so on the combinations of these inputs. So this is why it's called combinational circuit. And the circuit is designed to perform a specific operation. Yani, for example, you can have a combinational circuit that does addition or subtraction or multiplication. Okay, so you can design combinational circuits for that. So how do we design a combinational circuit? So the first step is called specification. So we start from the specifications. So what we need to do is that we need to specify what are the inputs, what are the outputs, what the circuit should do. Okay, this is given to us. For example, in a given problem statement, I will say design a circuit that has this number of inputs, this number of outputs, and it does this. So I can describe it with a paragraph. Okay, and this is called specification. So the specification is given to you. Okay, so you are supposed to look at the specification, understand the specification, and from this specification to go through the remaining steps, okay, of the design procedure. So we have the specifications. Now, once we have the specifications, we go to step number 2, which is called formulation. Now, the meaning of formulation is that you need to understand the specification, and from the specification, you try to convert the specification into a truth tables. You might actually have a truth table for every output of the circuit. The circuit might have multiple outputs, and therefore you need to have to convert the specification into truth tables. So this is called formulation. And also, you might also have like logic expressions for the outputs. Okay, so we try to convert the specifications into truth tables. That's the meaning of formulation. Now, once we have the truth tables, you might also have logic expressions, okay, for some outputs. What you need to do is that you need to do logic minimization. This will be step number 3. Like we have done, okay, before. You can use the Carnot map, you can also use Boolean algebra, or you can combine them, okay, to minimize the output functions. So you need minimal expressions, okay, for the outputs. So this is step number 3, which is logic minimization. Then after you have obtained these equations, then what you can do is that you can draw the circuit. Now, in the case of logic minimization, if you have multiple outputs, as we have seen in the previous presentation, is that you can extract the common terms and you start sharing gates. Then you go to technology mapping. Now you say what type of technology we are using. Today in modern technology, we are using CMOS. This is today's technology, which is used for digital circuits. So what you need to do is that you need to draw a logic diagram. You can draw the logic diagram using, let us say, AND gates, OR gates, inverters. Sometimes you need to use specific types of gates, like, for example, NAND, NOR. So this is mapping it to the technology. And then here you look at the cost, you look at the delays, you look at the fan in, the fan out. What's the maximum fan in, which is permissible, okay, for this type of technology? And we have a gate that has, let us say, 3 inputs, 4 inputs. That might be allowed, but 10 inputs, that might not be allowed, okay? So that will be the fan in. The fan out, similarly, you might actually have a fan out which is 2, 3, 4. That's okay. But having a fan out which is equal to 100, that's not allowed. So you have to start using additional buffer gates. So here you look at the cost, the delay, the fan in, the fan out. This is basically mapping it to the technology. And then once you are done, khalas, you have the circuit. Okay, so you have done the design, you have implemented the circuit. The last step is called verification. Verification means that, well, you have to verify your design, the correctness of your design. You have to ensure that if you provide the input, you will get the correct output. You can do this verification either manually by hand, okay, apply certain input, look at the outputs, and verify the correctness. Now that can be done when you are dealing with a small circuit. But when you are dealing with a large design, large circuit, okay, having hundreds or even thousands of gates, then what you need to do is that you need to use simulation. And for this purpose, we use Verilog to simulate and to verify the correctness of the design, okay? So these are the steps of designing a combinational circuit. We'll go through these steps, okay, and show to you how we can design a combinational circuit. My first example will be about designing a BCD to XS3 code converter. So first we have to start with the specifications. So what do I mean here by BCD to XS3? Well, the specifications like this. You would like to convert BCD code. Now we know what is BCD. BCD here is using 4 bits to represent 10 decimal digits from 0 to 9. XS3 is another code which also uses 4 bits to represent the 10 decimal digits. But we know that XS3 is that it adds 3, okay, to the value of each decimal digit. Yani 0 will be represented as a 3. Okay, 1 will be represented as 4 in binary. That's the meaning of XS3. Right. We say, what's the input? The input is BCD code from 0 to 9. What is the output? The output will be the XS3, which is also representing the decimal digits from 0 to 9. Right. So that's the specification. Now, we have the specification. From the specification, we have to go to the second step. What was the second step? So from specification, where do we go? What is the second step?
Formulation.
Okay, sorry, I did not hear you.
Formulation,
exactly, formulation. So that will be step number 2, which is formulation. Now, this can be done easily because we are dealing here with a small design. It's not really a large design. So we can do it easily with the help of a truth table. And we know that the BCD input is represented with 4 bits. So we can call them A, B, C, D. These are my inputs. And the output will also be 4 bits. This is XS3. So we can call the output WXYZ, for example. Now notice that BCD, okay, it only uses 10 combinations of A, B, C, D. So there is no 10 to 15. So these do not exist. These are not really BCD digits. So what we need to do is that we need to draw a truth table. So if the input is 0, 0, 0, 0, that's representing here the BCD digits 0, the decimal digit 0. Then the output will be 0, 0, 1, 1. That will be XS3. That will be the coding of the digit 0 in XS3. So we can go here from 0, 0, 0, 0, as indicated here. We can go all the way here to 1, 0, 0, 1. That will be digit 9. And notice that digit 9 is represented as 1, 1, 0, 0 in XS3. Just add 3 to it. So 9 plus 3 is 12, and this is 12 in binary. Now, the inputs 10 to 15, 1010 to 1111, these do not exist as BCD inputs. So for this reason, we do not really care what's the output, because the input here is not BCD, the output is not defined, and we can say that the output is a don't care. Okay, so that's indicated here with 4 X's indicating that the output is a don't care. So we can use don't cares in the truth table when the output is not specified. Okay, so that's formulation. We have obtained the truth table. What is next? We have the truth table. What should we do next?
Minimization.
Logic minimization, yes. طيب. What shall I do to obtain the logic expressions? How do I do logic minimization?
You can use either algebraic rules or
what do I need to obtain the equations? Yes, Ali?
Carnot map.
Exactly, Carnot maps. We have been talking about Carnot maps. So these Carnot maps are very useful actually for logic minimization. So let us use the Carnot map to do the logic minimization. So how many Carnot maps do I need here? How many Carnot maps?
4.
4. 1 for each output. So W will have a Carnot map, X will have a Carnot map, Y will have a Carnot map, and Z will have a Carnot map, right? So we need 4 Carnot maps. So let us draw them one by one. So this is logic minimization using Carnot maps. So I took the content of the truth table. So we have a Carnot map for W. I have a Carnot map for X, for Y, and for Z. Notice that the entries here, okay, so we have from 10, 11, 12, 13, 14, 15. These are don't cares. And the reason why, okay, they are don't cares because, as I said, okay, they are not defined, okay, when the BCD input is from 10 to 15. The output is not defined. So for this case, for this reason, we write them as don't cares. So what we need to do is that we need to now do the logic minimization. So I drew here the Carnot maps from the truth table. Just go back to the truth table. Look at the column of W here and draw a Carnot map for it. So this is here is my column for W. Okay, sorry for my handwriting. And draw the Carnot map for W. Repeat the same thing for X, for Y, and for Z. Make sure to enter the ones in the correct squares. You don't really want to make a mistake. Notice that column 1, 1 appears before column 1, 0. And also the row 1, 1 appears before row 1, 0. This is something which is very important for Carnot maps. Now let us do the minimization. We can minimize, okay, W, X, Y, and Z. Notice that some don't cares are combined with ones to maximize, okay, the size of the block. Some of them are uncovered. Yani, for example, many don't cares here are not covered. That's fine. You can just keep them as zeros. You don't really have to combine them with ones. Now write the equations. So we obtain here 4 equations, okay, for W, for X, for Y, and for Z. So we have the 4 equations. We have the equation for each one of these outputs. Okay, is this clear? So that's basically what needs to be done. Okay, and step number 3 is to obtain the equations. Use the logic minimization. Use the Carnot maps to do the logic minimization and obtain the equations. Okay. Now, what you can do is that because we have multiple outputs, is that you can use the properties of Boolean algebra to extract the common terms. Now that's interesting, is that we can go into a third. Now what we have seen is the sum of products. Sum of products are 2-level expressions. So you have the level of the AND and you have the level of the OR. But you can actually add a 3rd level. Now notice that here we have B, C, B, D. So I can write it as B and C or D. Now, the reason why I'm doing it is that here I also have B prime C, B prime D. So I can write it as B prime C or D. So I can extract common terms, okay, using the properties of Boolean algebra. So that's interesting. Also here, notice that this is B, C prime, D prime, but C prime, D prime is the complement of C or D. So it's C or D between parentheses prime. Again, we have C or D. Okay. And finally, okay, in the last, well, that's actually is for X, for W, for X. How about for Y? Notice that also C prime, D prime can be written as the complement of okay, C or D. So in other words, we can use C or D as a common term, okay, which may or may not be inverted. So now the step number 4 will be technology mapping. So we have obtained the equations using the Carnot map. So what we need to do is that we need to draw a logic diagram using the AND, OR, and inverters. So let us do this. Okay, so this is now, notice that how C or D. So C or D, this gate here is shared. Notice it's fan out, okay, how it is shared. So it's used here by W, it is used by X. So notice that how the output of this gate is connected to the input of this gate, and this inverter. Now this inverter will give me C or D prime. So, and then it is also shared by this AND gate and by this OR gate. Okay, so we have drawn the logic diagram using AND gate, OR gate, and inverters. In fact, we can also use other gates. Yani, for example, we can use NAND gates, NOR gates, and XOR gates. If you look at the equations, okay, from the previous slide, I'm just copying them. When you look at B prime, C or D, or B and C or D prime, that's actually XOR. It's B XOR C or D. So for example, we can substitute, let us say C or D with a certain, let us say term T is equal to C or D. And we can XOR B with this term C or D. And therefore we can use the XOR gate. Similarly here, we can use the exclusive NOR. So we can take here not the exclusive or I can just take it the XOR with D prime. And if you do it like this, you can even do more simplification using the XOR gate. So that's interesting, knowing the properties of these gates, understanding the properties of the XOR gate, the exclusive NOR, extracting common terms. So you can do all of this. So the Carnot map will give you the minimal sum of product or minimal product of sum, but understanding the properties of Boolean algebra and understanding the properties of other gates, like the XOR gate, you can do further simplification. Okay, and I can rewrite these terms a lot simpler, okay, than those which are obtained using the minimal sum of product expressions using the Carnot map. طيب, do you have a question about this example? That's how we can design a BCD to XS3 code converter. This is step number 4, which is technology mapping. We still have step number 5, which is called verification. Now, verification, you have to ensure that this circuit is going to work properly. So you have to ensure the correctness of your design. The way that you do verification, you can do it either manually by hand. You apply inputs and you look at the outputs, and if the output matches the output in the truth table when we did the formulation, so you match the output of the circuit against the truth table that you have obtained with formulation, then in this case you have a correct circuit. You can also use a simulator. You can describe your circuit with a simulator. You can, you can describe your circuit in Verilog, and you can use a simulator to simulate your description, your hardware description. And if you have, you can observe the output, and you can observe the waveforms. You can check the output. If they match the output in the truth table, then you have the correct, then the circuit is performing correctly. So basically, you have verified the correctness of your circuit. If we look at the circuit here, we look at the equations for W, X, Y, and Z. We can derive the truth table of the circuit diagram. So we can do this manually. And after deriving, okay, the W, X, Y, and Z for all the BCD inputs, A, B, C, D, then we can check, does this match the truth table that we have obtained from the specifications? If it does, then we have the correct circuit diagram. Okay, so in this case, you can actually easily verify from the equations that we obtain directly from the circuit diagram that we have the correct truth table. It matches the truth table that we obtained from the specification, and therefore we have verified the correctness of this circuit. So this circuit does a BCD to excessive 3 conversion. I'm going to give you a second example, which is about BCD to a 7-segment decoder. I talked about an example last time about how to convert from BCD to excessive 3. That was my example number 1. So this is example number 2. Okay, so what is a 7-segment display? It's a simple display which is used in some digital clocks, some calculators, some electronic devices. You can go and buy it from, let us say, electronic stores. It's a small display. It has 7 segments. And these segments are light emitting diodes. Yani you can turn each segment on or off. By turning these segments on and off, you can display the 10 decimal digits from 0 to 9. So the segments here are named. You can see here lowercase a, okay, that will be the top segment. Then you have B, then you have C, and then D, E, F, and G. So the G is this segment, okay, in the middle. Okay, that is the segment G. So these are my 7 segments, and each segment can be turned on and off, and you can display the 10 decimal digits. So now the question is, or let us say the specification is, we want to design a BCD to 7-segment display. So my input is a BCD code here, capital A, capital B, C, and D. So this will be a BCD decimal digit from 0 to 9. And the output will be the 7 segments from A to G. Notice that I'm using for the inputs capital letters to distinguish this from the output. We can, of course, name them differently. Of course, we can use, for example, for the input, I can call them WXYZ, for example. It does not really matter. So I'm using capital letters to distinguish the input from the output. Okay, so this is the problem, okay, that needs to be solved. I need to design this, this box here, which is the BCD to 7-segment decoder. So the input is BCD, the output is going to generate 7 outputs for the 7 segments in the display, and we can turn on and off each segment separately. That's really the BCD to 7-segment decoder. This is what it does. So we start with the specification. So the input here consists of 4 bits, and it is BCD code, and I'm naming it as capital A, B, C, D. And the outputs are 7 bits, and these are lowercase a, B, all the way to G. So these are for the 7 segments. And the display should be off if the input is non-BCD. Okay, so the BCD input will be from 0 to 9, but because we are using 4 inputs, 4 bits, then we might also have from 10 to 15. These are non-BCD inputs. So here in the specification, okay, it requires us to turn off the display if the input is non-BCD. So we don't really want to use don't cares. No, we would like to have zeros, okay, in the output, indicating that these light emitting diodes, these 7 segments should be all off, turned off. So this is my specification. Now, what is step number 2? What comes after specification? Students?
Formulation.
Exactly. So how do we do this formulation?
Constructing a truth table, I guess.
Exactly. So we need a truth table. So let us draw the truth table. Okay, this is called formulation. So we write all the 16 combinations because we have here 4 inputs, A, B, C, D. So we have 16 entries in the truth table. So we have the 10 BCD inputs from 0 to 9. So this is 0, 0, 0, 0. This is digit 0. This is 1, 0, 0, 1. That will be digit number 9. And if the input is non-BCD, it is shown here at the bottom. So these are 6 entries in the truth table, which are from 10 to 15. Now the outputs, we have 7 outputs. So we have 1 column for each output. Now the outputs here will be for these 7 segments. So for example, if the input is 0, 0, 0, 0, I should display the digit 0 on the display. So digit 0, this is how it appears on the display. So A must be 1. So segment A must be turned on. Segment B must be 1. C must be 1. D1, E1, F1, G is 0. Now remember that the G is this segment here, which is in the middle. So we turn on all these segments except the one which is in the middle. So this is called formulation. I should actually say that for each input, what should be the output? And this is done using a truth table. Okay, notice that, for example, if the input is 1, I should display only these 2 segments here, okay, which are B and C. All the remaining segments are zeros. If the input is 2, notice that which segments here should be turned on. So it should be A, B, C should be 0. Okay. And then we have D, E, F should be 0, and G should be equal to 1. Okay. So you see that these are the segments, okay, that should be turned on for 2, and so on. So what we have to do is that we have to show that which segments are 1s and which ones are 0s for the 7-segment display. Is this clear? So this is the truth table for our decoder. Students, any question?
Yes.
So you can see that if the input is not BCD from 10 to 15, the specification indicates that all the segments should be turned off. So they should all be zeros. So I did not really use any don't care here. I wanted them to be on. So if, for example, if for whatever reason, we get an input which is not BCD, we are not going to display anything. So we are going to turn off this display rather than displaying some kind of random segments to turn them on and off. No, we will actually turn them, all of them off. So for this reason, I did not really use don't cares. I forced all the outputs to be all zeros. So this is actually in part of the specification. It says that the display should be off for non-BCD input codes. Okay, is this clear? So you have to go according to the specification. You cannot just put don't cares randomly. No, you have to look at the specification and see what is the specification, and then accordingly you can come up with the formulation, with the truth table. Okay. Fine. What is next?
Logic design.
Yes, we need to go through logic minimization. So how many Carnot maps do I need?
You need one for each A, B, C, and D. 7.
So we need actually, we have 7 outputs. Each output is a function of the 4 inputs. So for this reason, we need 7 Carnot maps, correct? So we need 7 Carnot maps, okay, from this truth table. So let us do this. So I'm going to draw the first 3 Carnot maps. This is for output A, B, and C. So for these are the first 3 outputs. And we just need to copy, okay, these columns. So this is column A here. Let me see if I can highlight it. So this is output A. And we have to fill the 1s and the 0s inside the Carnot map, as indicated here. So I'm leaving here the 0s as a blank, just showing the 1s inside the Carnot map. So we do it actually for output A, we have the Carnot map for output B, and we have the Carnot map for output C. We still actually have up to G. So these are not all the Carnot maps, these are only 3 of them. And we obtain a minimal sum of product expression. Now notice that the expressions here are unique because the prime implicants are essential prime implicants. So we don't really have multiple solutions. We only have a unique solution for A, a unique solution for B, and a unique solution for C. Okay. طيب. We need to continue. We have to obtain, of course, D, E, F, and G. We still actually have 4 more outputs. So we still actually have 4 more Carnot maps. We have to get all of them. Now, what should we do here?
Try to find common terms.
Exactly. Common terms, extract the common terms. Can you see something which is in common? Yes, Muhammad.
B prime and C.
B prime, C prime.
Yes, B prime, C prime. It's very clear. It is really common. So really what I would like to do is that I would like to use now extract common terms because we have multiple outputs. And by extracting the common terms, I can share the gates and I can reduce the cost. That's what I would like to do, okay? Now notice that B prime, C prime is very clear. But if you look at the other terms, you can also see that sometimes things are not really exactly identical. Yani, for example, when you look at A prime B, it also appears here as A prime B. When you look at A prime D, or let us look at B prime C prime, it also appears here as B prime C prime. So we can even extract even more, even though the term is not really identical. Okay, so sometimes the term can be part of a longer term, so we can still extract it. Notice that A prime D, it appears here. This is the A prime and this is the D. Okay, so we can extract a lot of common terms. So we can define these common terms. We can say that let T1 equal to A prime B, let T2 equal to B prime C prime, let T3 equal to A prime D, and rewrite, okay, more optimized logic expressions using the T1, T2, and T3. So I can write C as T1 or T2 or T3. Notice that T2 appears here. Notice that T3 appears here. Here I have T1 and D. Here I have T2 and A. Notice that B prime, C prime also appears here. Okay. And here I have also T2 and D prime. So you can see there is some kind of sharing, okay, of terms among these 3 outputs. We still actually have more outputs. So maybe I can even share more. So let us go to, okay, we still have 4 more Carnot maps, okay, for the remaining 4 outputs. So we have the Carnot map for D, for E, for F, for G. So we can, again, we need to do logic minimization. write the logic expressions and extract the common terms. Now, sometimes the common term is very clear. It is obvious. Notice this red block. It's the same place. It's the same term appearing in different outputs. Okay. Notice this blue one. Okay. It's the same blue one here. The same blue one here. Notice that this, okay, this is the pink one. Okay. So some of these terms are very clear. They are the same, they are identical. So I can actually extract them directly from the Carnot maps if you want. Or you can write the expression and then you can extract them from the expressions. So now, when I would like to write my optimized logic expressions using these common terms, they become very simple, very easy. Notice that T4 is actually this red block. T4 is A, B prime, C prime. That's T4. Okay, that's the term for T4. It appears in D, it appears in F, it appears in G. Okay, notice that T5 is this blue one. Okay, so that's the blue one, which is shown here. Okay, that's T5. It is B prime, C prime, D prime. It appears in D, it appears in E, and in F, and so on. Okay, this orange one. Okay, look at this orange one here. It appears in D and in G. So this is defined as T6, A prime, B prime, C. Notice that where it appears in D and in G, and so on. Okay, so that's really the idea, is that to extract these common terms and reuse them, okay, share them by different outputs in different expressions. So that's really the idea. So whenever you have multiple outputs, there is actually a chance that you will have many common terms, okay? And sometimes if it's not really identical, look at T8, for example. T8 is A prime, B, C prime. So that actually is T8, which is shown here. This is actually is T8. This is also T8, okay? That's T8. And notice that this one is just a minterm, but it can actually, it is part of T8. So therefore it can be written as T8 and D. Notice that T8 is shared by F and by G, but I can write the minterm as T8 and D, okay? So when you write the term for this, when you write the minterm, algebraically, you will find it is T8 and D. And T8 is nothing but A prime, B, C prime. Okay? Did you get this? So we have the optimized logic expressions. So we have obtained all the logic expressions. We have extracted all these common terms. So let us rewrite all of them. Okay, so we started from T0, we went all the way to T9. So these terms were extracted, and we wrote these optimized logic expressions from A to G. So we have 7 outputs. These are their expressions. So what we need to do is that we need to do the technology mapping. So we are going to use just AND gates, OR gates, NOT gates, inverters. Sometimes the question might ask you to use other types of gates, but this is actually very simple here because we're just using AND, OR, okay? And also we have inverters, we need inverters. So let me show you, okay, the output for E, F, and G only. Okay, let us just take a look at these 3 outputs. Of course, we need a larger place. I mean, we need more space to show the entire circuit. But just to illustrate to you, okay, the idea of generating all of these terms. So first, we need actually to generate all the terms from T0 all the way to T9. But let us take a look here at E, the output E. So the output E is T7, T5 or T7. It's this expression here. So this is T5. and this is T7. Okay, and I just need one OR gate. Notice that T5, what is my expression for T5? It is B prime, C prime, D prime. So this is B prime, C prime, and I need another AND gate to end it with D prime, and the output will be T5. The output of this AND gate here will be T5. Notice in the case of T7, the term is here. A prime, C, and D prime. So this is A prime and C. Notice that A prime and C, we gave it, this is term T0. And for example, the output A uses this term T0. But T7 is nothing but A prime, C, and D prime. So we take T0 and we end it using this AND gate with D prime, and I will get the output here, which is T7. So we have two levels of AND gates, and we have even two levels of OR gates. Notice that for the output F and G, for these two outputs, F and G, notice that I have T4 is in common, T8 is in common, and T9 is in common. So T4 or T8 or T9, I can use this OR gate here. This is T4, this is T8, and this is T9. I can actually OR it, and I can share this OR gate here, this 3-input OR gate, by F and by G. So basically, this F is going to use a second level OR gate to OR the output of the 3-level OR gate with the T5. So all what we need to do is just OR it with T5 and you get F. And if you OR it with T6, you get the G. Okay, so we OR it here with T6. So these things are used, okay, by circuit designers. And the idea is to share gates. And by sharing gates, we can reduce the cost. Okay, so we use the Carnot map to do the simplification to obtain minimal sum of product expressions. And then we extracted the common terms. And then once we have extracted the common terms, we can start sharing these terms. And of course, by sharing these terms, we are sharing gates among these outputs. So this is my design. This is, of course, this does not really show all the 7 outputs. It is just showing the last 3, just to illustrate to you. But of course, we need all the remaining outputs. We still have to add them to this circuit to make it complete. So this is my BCD to 7-segment decoder. Questions? Are we done? Yes, Muhammad.
Is it always best to start by creating the, for example, the common terms in T0 to T9, or do I try to find the ones that are similar from the outputs?
Well, first find those which are identical, and once you find those which are identical, for example, in F and G, you can see that T4 is identical, T8 is identical, T9 are identical. So these are very clear. Okay, so extracting them is obvious, but then you might actually find that T0, okay, which is A prime and C, which is used in A, T0 is actually a subterm of T7 because A prime and C also is included here.
Yes.
So rather than using actually a separate AND gate, okay, for T7, you can use the same T0 and end it with T prime. That's also is a small trick that we use it.
Okay.
Okay. Type. What is missing? Are we done? There is step number 5.
Verification.
Verification. Well, we have obtained equations, but how can you say for sure that this circuit is going to produce the correct output that I need? Okay, we still have to verify the correctness of this circuit. So I have the circuit, I have the equations. Please verify. Okay, so this verification step is very important. Either we can do the verification manually, and this is done by analyzing the circuit. You can look at the circuit, you can look at the equations, these equations. You can apply all the possible inputs, and you can look at all the outputs, and you see if these outputs are the expected outputs. If they match the truth table that we obtained in step number 2 in the formulation step. So we can compare the final circuit truth table against the specification truth table, the specified truth table that we obtained in this second step, okay, in the formulation step. So if these are identical, then we have verified the correctness. So this can be done manually. This is easy when you are dealing with a small design. So relatively speaking, this is small design. It's not a large design. But it becomes tedious if you are dealing with a large circuit, with large combinational circuits. It becomes actually very tedious, and the humans can make errors. So for this reason, we go to simulation. So simulation is that we can describe the circuit in a hardware description language like Verilog, and then we can simulate this final circuit. So by doing simulation, we have the description in Verilog. We can write a test bench, and the test bench can automate this verification process. We can supply all the possible inputs. Okay, so this is called exhaustive testing. You provide every possible input to the circuit, and you can check the output. Now, the outputs are known in advance. So what you have to do is that you have to verify that your circuit is producing the correct output. This is the meaning of verification. So you are actually testing, you are checking that your circuit is functioning properly, is producing the correct output. Now, exhaustive testing depends, of course, on the number of inputs that you have. If the number of inputs is small, it can be done. But if the number of inputs becomes very large, then exhaustive testing can be very time consuming when you have a large number of inputs. Right. So let us now model, okay, the 7-segment decoder that we have seen in Verilog. Now, we're not going to model it at the gate level, okay? That will be very tedious, okay? Although we have learned about gate level modeling, I'm going to use continuous assignment. That will be a lot easier. So we are going to define a module, which is called BCD to 7 segment. So this is the name of the module here. And this module has 4 inputs, capital A, B, C, D, and it has these 7 outputs. Remember that Verilog is case sensitive. So therefore, when you write capital letters, okay, for the names of inputs and the names for outputs, okay, they are different. So capital A is different from lowercase a. So you can use these 2 different cases if you would like to distinguish the input from the output. If you don't like to do this, you can use different letters, of course. Right. So after that, inside the module, we describe all the, we need actually some, remember that we have these kind of common terms. Okay, so we have extracted these common terms. These will be wires. So you have to declare them as wires from T0 to T9. And then you can use continuous assignment to assign the expressions, okay, for T0 to T9, all the way to T9. So I don't really have here much space in this slide. So I'm using here multiple statements on the same line. That's okay. You can do that as long as each statement is terminated with a semicolon. So we can write, okay, the terms. So for example, T0 will be not A and C. So that will be A prime C. So remember the syntax. You have to use the right syntax in Verilog. T1 will be A prime and B. So not A and B. Notice the not operator. Notice the and operator. And so on. Then we have to assign to the outputs. Again, continuous assignment. So A here, this is output A. It will be T0, or that's the or, T1 and D, or T4, or T5. Okay, so we just described them with expressions, Boolean expressions. We use the operators which are provided in Verilog. So this is very easy. We can model this BCD to 7 segment decoder very easily using continuous assignment in Verilog. Okay. Well, what is left is to test the BCD to 7 segment decoder. So we're going to write a test bench. Inside this test bench, remember that the test bench does not really need any ports. So there are no inputs, no outputs for the test bench. So this is the name of my test bench here. You can call it any name. For example, I'm calling it test BCD to 7 segment. And then you have to declare your inputs as variables. So notice that here variable means of type register. Register means variable. And the outputs will be wires. So we have 4 inputs, we have 7 outputs. Again, they don't really have to match the names inside the module. You can give them whatever names. And then you have to instantiate the module to be tested. Okay, so here, this is the name of the module of my design, BCD to 7 segments. This is the name of the instance. These are the inputs. These are the outputs. So they have to be in the same order that they appear in the design module. Okay, and then we can write an initial statement. And inside this initial statement, you can provide, okay, all the test cases. You can do it exhaustively. Okay, so we start at 0, 0, 0, 0, and then you can end at 1, 1, 1, 1. Suppose that every 10 nanoseconds, I would like to change the value of my input. So what you have to do is that you have to write lines here. Every 10 nanoseconds, let us say you start by changing D. So you start 0, 0, 0, 0, then after 10 nanoseconds, you would like to have D equal to 1. So it becomes 0, 0, 0, 1. Then after another 10 nanoseconds at T equal to 20, then you would like to have 1, 0. So you make C equal to 1 and then D back to 0. And then you have 1, 1, and so on until you reach 1, 1, 1, 1. Now there is another way of doing it. Okay, you can write all of these statements inside the initial block, and these are all your test cases. Or you can use actually the help of the always statement as shown here. In fact, it can be done in different ways to generate all of these test cases. Okay, I'm going to show you a trick here, or not a trick, yani, one way of doing it in Verilog, which is using the always statement. Now think about here, we have 4 always statements. The meaning of always is like a continuous loop. Okay, so always is used to model circuits, but I'll talk about it later in great details. I'll come back to it. But in this example, I'm using the always to generate, okay, the test cases. So think about each always statement here as an infinite loop. So every 10 nanoseconds, we are changing, we are inverting the value of D. So initially D equal to 0. After 10 nanoseconds, D becomes not D, which means that it becomes 1. And then after another 10 nanoseconds, it becomes D becomes not D, so it becomes not 1, becomes 0. So basically it was initially 0, then 1, then 0, then 1, then 0, then 1, and so on. Okay, so that's what it means. In the case of C, we are actually changing the value of C every 20 nanoseconds. Okay, so it means that initially C was 0, and then after 20 nanoseconds, it becomes 1. And then after another 20 nanoseconds at T equal to 40, it goes back to 0, then 1, and so on. The same thing for B, the same thing for A. But in the case of B, we are delaying it by 40, and in the case of A, we are delaying it by 80. But if we write a test bench like this, now notice that these 4 always statements are running in parallel, as if they actually are 4 parallel statements inside the simulator. So what we have seen in the previous slide, we have seen an initial block and we used also the always statement. Okay, so in the case of the always statement, we always use a delay here. So notice that we are using a delay to delay the execution of the statement. Okay, so always itself can be a block. It can be much more complex than this. I'll come back to it later in a later presentation when I talk more about advanced topics and more intermediate concepts about Verilog. But for the time being, we are just using it inside the test bench to generate all the test cases. I would like to have exhaustive testing. So both the initial block and the always block are called procedural blocks in Verilog. These are the two different types of procedural blocks in Verilog. And they are called procedural because the body of the initial and the always are procedural. So we can write procedural statements inside them. Notice the hash delay. I use it to delay the execution of the procedural statements. So we delay the execution of the procedural statement. So you can have multiple statements inside initial block. You can have multiple statements inside the always. So you can surround them by begin and end. So here we had 4 always statements. Each one had only one statement. That's it. And you can have multiple procedural blocks, multiple always statements that can run in parallel inside the simulator. So now you can run the simulator. This is actually, I'm using it on Logisim. You can use EDA Playground. You can write it. You can test it. So you can see that here my inputs A, B, C, D. Notice that how D is changing. So initially D was 0. And then it becomes 1, then 0, then 1. And this is changing every 10 nanoseconds. So here actually my time scale is 1 nanosecond. And then notice that how C is changing, okay, from 0 to 1, okay, every 20 nanoseconds. So 0, then 1, then 0. So notice that every 20 nanoseconds we are changing C. Then every 40 nanoseconds we are changing B, and every 80 nanoseconds, we are changing A. So once we reach this time here, which is 160 nanoseconds, we have generated all the 16 cases. So notice that initially we have 0, 0, 0, 0. Then we have 0, 0, 0, 1. Then we have 0, 0, 1, 0. Then we have 0, 0, 1, 1. So at the end here, we get 1, 1, 1, 1. So this way, we have generated all the 16 test cases. And then we can look at the outputs, okay, A to G, and we can verify that we are getting the correct output. So notice that when the inputs are zeros, notice how the outputs, so this will be 1, 1, 1, 1, 1, 1, 0. Notice that only segment G is 0. That will display the digit 0 on the 7-segment display. So you can verify all of this with the help of the simulator. Any question about this? Right, so we have seen this. Yes, Muhammad, تفضل.
The delay on the always is based.
It's very important, yes.
Yeah, because so you made it in a way that it's similar to how the values change in the truth table, right? So they're
so the way that
0,
I
0, 0,
selected,
0.
yeah. So if you go back here, I always doubled. Yani for example, this is 10, this is 20, this is 40, this is 80. So basically, I changed the delay because if I use the same delay, then all of them will change at the same time. So I wanted actually them to change at different times so that I can generate all my 16 test cases from 0, 0, 0, 0 all the way to 1, 1, 1, 1. This was the trick, which I did, is that I just used different delays here.
Okay, thank you, sir.
All right.